firstly, let's define a random codebook. This is probably, the idea of a random codebook is probably the core of the channel coding theorem. Without it, we probably can't make any arguments like this. So the idea that the codebook is itself a random variable is extremely powerful because it allows us to use all of these weak law of large numbers arguments. So this is also why the input probability P of x is important. So fix P of x. And generate a 2 to the NR n codebook at random according to P of x. What do I mean by that? What I mean by that is that the codebook looks like this. So the codebook is the set of all code words. So we can represent it as a matrix. So the first code word will have elements x1, 1. The subscript will be the element within the code word, and the thing in brackets will be the index of the code word. So x1 will be x11, x21, x31, and so on up to xn1. So this is a 2 to the NR n code book, so the length is n. x12, x22, x32, and so on, xn2.
The argument, the argument represents the message from the index of the message.
Exactly. So this vector is the code word corresponding to message 1. This code word is the code word corresponding to message 2. So on. Finally, x1 to the NR, x2 to the NR, x3 to the NR, so on, xn to the NR. This is the code word corresponding to the 2 to the NRth message. So there will be 2 to the NR rows and n columns. So this is basically a set of code words, right, where the code words exist on the rows. So if I want to send message k, I just go to the kth row, and that's my code word. So the idea is each element, each xij, is chosen IID using P of x. So that's a random code book. All of the elements in that matrix are chosen at random. Okay, now that at first that seems really weird because, for example, there's absolutely no guarantee that no two code words will be the same. For another thing, even quite apart from two code words not being the same, there's absolutely no guarantee that this code is going to be good, because we're literally picking it at random from all of the possible entries that could go in any row. We're literally picking all of them, picking from them at random. What's going to save us is that typical code books are good, which is actually quite a surprise. So the power of the random coding argument is that because of the properties of typical sets, if n is sufficiently large, a typical code book is actually quite good. Typical code books will have rows that tend to be quite different from each other. So these code words will tend to be quite distinct and will therefore actually serve quite well as code words. So the probability of a particular code book is, let's call it P of C. It's the probability of a row of rows from 1 to 2 to the NR. Excuse me, product of the rows from 1 to 2 to the NR, product of columns from 1 to n of the probability of X at row R and column C. So that is a random code book. I think that is probably a good place to stop for today. I will continue my description of the exact definition of the transmission reception scenario on Tuesday. Any questions? So, the mathematics are going to get fairly intense for the next couple of classes, but in the end, it's not really that hard. Basically, what information theory is about is counting. So, as long as you can count elements of the typical set and argue that, basically what we're going to do is we're going to argue that the probability of error goes to 0 as long as the set of things that I can confuse with my original code word is not terribly big. So that's basically the argument that I presented at the end of talking about the joint AEP, and really that's the thing to bear in mind. So I will see you on Tuesday.